Welcome to a new test and teardown video. This time it's another HP 5223L electronic counter. And yeah, you got it right. Nixie tubes are in here. I love Nixie tubes. Why can't we just... It's really bad. This is so dark. But anyway, this is a very nice counter in super good condition, and seems to be from 1974, plus minus a little bit. We got two inputs, and the two inputs are called A and B. And they can be AC or DC, and volts can be from 1 to 100 and all that. Slow, positive, negative. And this is of course needed because this thing can actually measure start and stop and ratio and all those things, time interval. So it's a very advanced counter. It's not just a frequency counter like almost anything else, right? And so of course the time base, you can have 1 second, or I don't know, very small time intervals. And the time is multipliers if you're in period or in ratio. Okay, it's gonna be the red numbers. So far so good. We got some sample rate, and it goes from fast to hold. Okay, and power off in one button. This is probably an indication of gating. Yeah, let's look at the back side. So I see a fan. Oh, we got some storage. Time base. Frequency standard. What exactly is the difference? Digital recorder. And the filter looks quite clean. Marker A and B. What the hell is that? And okay, so it's running at 35 volts internal voltage, and we got a mains supply here, 0.5 amp. Okay, and selector is correct. All I have to do is find my plug, and then we are ready. That's gonna be interesting. So I think we're ready to apply mains. Nothing bad happened, and it's alive. Whoa, we got reset. It's also working, but that's a really beautiful picture. Maybe the one in the middle is a little bit dimmer. I don't know. Hey, let's try and input something. So we're gonna go in frequency. Exactly. Look at that, 1 second. That's what it says here. This one is blinking. And it says kilo. So this is kilohertz, point hertz. Really? So let me give you 1 kilohertz. And I don't... Yeah! Look at that! So that's interesting. What if I say 1, 2, 3, 4 hertz? So it's... Okay, it takes a little bit of a while before it shows up. That is a little bit funny, isn't it? It's funny it says kilohertz. It could have said just hertz, right? And then why do we need this? But hey, how about if we say 1, 2, 3, 4, 5 hertz? Is that going to work? Blind. I mean, it's actually really good, and it works. And so how about, so this is as, aha. And you don't see the counting up, so that means this one is double buffered. Don't you just like that? So this is a very, very much improved design. Let me dial the 10th. See, dial. So every second I just get a new number. You don't see the counting up. One, two, three, four, five. We're back. And then it comes like this, right? So this is really getting interesting. I will try and see if I can figure out how to set up this AB. Hey, how about if we go, okay, period. That is going to be funny, right? So if I say 1 kilohertz, okay, that is frequency. So let's go in period. So that is 1 millisecond. And then it goes blinking fast. And then I go 1 millisecond. No. What am I doing wrong here? Aha, so this needs to be faster or what? It needs more time or what? What am I doing wrong here? Yeah, it was me. That was dumb. Of course, this is the time base. So, of course, I need a 10 microsecond pulse, and then I am using my 1 kilohertz of input signal as the gate. So now this is the gate, and then it will count to 100, and that will be 1.00 millisecond. So let's say, hey, maybe I can actually input my frequency in time. Yeah, let me see if that is possible. No. So if I say 5 kilohertz, yeah, it's 0.2 milliseconds. So that works as well. And what if I say 100 hertz? That should be 10 milliseconds. So all in all, that is really good. Hey, how about if I take a very, very slow, like 10 hertz, 100 milliseconds. Ooh. Now we see some blibbity-blobbity update. I mean, this is very useful. And it looks really, really nice too. This is very, very crazy. You know what I can do with this? I can take the ratio AB, okay, and here is a multiplier for the one that is used for the time base. So that is B. B is now the time base, right? Or the gator, so to speak. And the fun thing is, here on A, I got 100 hertz, and here I got 1 hertz as my gator, okay? So of course this one is 100 times faster than the other one, and I can get a decimal on this because I'm just dividing the 1 hertz by 10. So I'm counting, so it now takes 10 seconds to measure the ratio of A versus B, and that of course gives me 10 times higher resolution. It just takes 10 seconds to do the ratio. Wow, this is so nice. Of course, if I go back ratio 1 every second, I will know A is 100 times faster than B. And so that means I can use external gating, external time basing, or whatever I kind of like. Now I got a frequency counter with any other kind of gates, whatever I want to gate or how fast I want to gate. Yeah, I can do that as well. I mean, I really like this instrument. It's super, super nice. It was definitely ahead of its time. So in case anybody asks, this thing uses about 35 watts. And now we're gonna open it and have a look inside. So this is the inside, and everything here is full of a nasty layer of, look at that, let me get some light. Ugh, some gross stuff, and it's just all over the place. And look, this is what happens. Ugh. I need to go and clean this up because this is not good and I don't want to have this in here. So yeah, we need to play with compressed air again, and then we can clean this up. Let's look a little bit on the inside. Now it is nice and cleaned. So here's the function switch and the time-based multiplier. So I guess all this time-based stuff goes down here to all the counters, and so that will be some pre-counters before the real counters. What is all this stuff doing? Time basing probably, right? And everything is in nice sockets. So, and we got some names and we got some numbers and all sorts of stuff. That is really, really good design. The only thing that I see here is a 100 kilohertz crystal, and of course it's adjustment. But why isn't this in a nice little shielded closed cabinet in here, so that fan temperature is not gonna go and affect this? It should be, you know, located and isolated, or even, you know, with an oven. But again, this is very low frequencies, very low resolution, only 300 kilohertz. But again, okay, 300 kilohertz plus minus, you know, we can go 10 seconds, right? So this is 0.1 second to 300 kilohertz. So I bet we could easily see a temperature variation on the crystal and get a few counts off. So what have we got over here? That will be the power supply. See, we got all sorts of rectifier diodes and stuff. But what is that? I'm not really happy about that. So this is a modification. And if you look at the color and thickness of this wire, and if you look over here at the fan, so I believe this is the wire. And what are they doing? They're putting a capacitor in series with the fan, so it's going to run slower. Hee hee. But it's still a little bit crusty. Got some capacitors, the voltage regulator. So this will be the input. And again, nice sockets. So this is, can we get this up? Come, yes we could. So probably the first board will be what, amplifier, and then we got some trigger level things. Let's have a look. Beautiful with the sockets and all that. I really like it. It's super duper service friendly. Hui. Those are located very, very close. I would say, if I didn't know better, they're touching. Those two are touching and those two are touching. Ugh, nasty, nasty. They're probably connected, you know, can is obviously the same signals, right? But that's probably a hysteresis or trigger board with this variable. Yeah, here it is, variable trigger. So that will require a few transistors, and they're of course running them a little bit hot so they go fast. So that is of course the trick. And if I am not very much mistaken, that will be so. Let's have a little look at the, so you can't pull this up. So that will be locked due to this? Is that how it is? Or is it just me? Really? I have to pull a half a megaton. Okay, here we go. So that is definitely the power supply. Don't you just love this kind of layout where you have so much space? I really enjoy this layout style. Look how you could easily have made this board half the size, right? And this is not how we do it today. It's always small as possible. Ooh, as small every time. This one was hot. Or was fixed. So that one is great. Let's have a look at, I think this is the same board as the others, right? And again, they are really, come on, man. Oh, let's see what that can do. A little diode and some stuff. I better go and see if I can find some better schematics or something, but I really, it wasn't that easy. People want money for service manuals and for schematics, and that is not gonna happen. Nope. We don't work like that. I really want to get those out and have a look. So this one can count to 10. So how is that done? This is done. Ooh, I see what I see. They have stolen the same kind of counter ideas. So you got 4 and we got 4. They're probably doing exactly the same as their older equipment with the neon bulbs, and this is like Charlie plexing, and then they go to the Nixies. Oh, that's probably what we see. And we've got some diodes here to make it into a Nixie kind of drive style. Oh man, I love it. Oh yes it is. That is exactly what it is. Yes, they are doing that. Exactly the same thing. And you know what that is? So that is the sort of Charlie plexing neon bulbs, and the neon bulbs drives LDRs, and the LDRs drives the Nixies. Yeah, that's how it is, right? This is exactly how it is. We gotta go in here. So this is one of the counter and display units, and it is of course super beautiful. And here we've got 10 neon bulbs, and they're connected to the counters, made now with transistors instead of tubes. And what do you know? March 1966. So now we know the exact age. We're gonna go in here and have a look so I can prove my point. So now we're inside the counter unit. Let me see if I can show you guys this. So this is the Nixie with its 10 cathodes that lights up. And see, they're connected to this resistor element here with the different sensitive elements like this on a printed circuit ceramic board. And then you have the counter neon bulbs that activates the different sensing elements. It's really fantastic. So I have to put this all back together. be sure nothing is gonna break. So this purple wire was in this hole, no problem. I will restore this. It seems like it's impossible to find good schematics of the model 5223L, but what I can find is quite a lot of other models that looks a lot similar in the counter system. For example, the 5245L, it consists of the same binary counters as you see here, and they even have a full counter block schematic of this of the 4-bit counter. So this is what you saw on the PCB, the 8 transistors needed, because we got 2 of them in each of the binary counters. So that will be 8 transistors, and this is how they are connected to count to 10. So this is how it works. They have invented their own little binary code, so it's not the normal as you see here, 0, 1, 2, 3. Oh, that is quite normal, but then it goes, oops, that is 4, this is 5, and then it goes a little bit funny. Okay, so this is why are they doing this, and this they're doing this because then they can light up the neon bulbs and drive the neon Nixie tubes. So this is really genius. And yeah, I think they explain a little bit more here. You have lamp circuits, la 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 la. If you want to know more, of course, you can go and read this this PDF. I finally found a little bit more very useful information. This shows the neon bulbs and the counters I already talked about. See, this is the photoconductor plate. And see, that will be this light sensitive elements. See, this is really interesting how you need to add light to turn on and off the different elements. So when you can now you can actually see this, right? Try and imagine those LED neons and those neons, they're connected in the lines down here, right? And then they shine light on the different sensitive elements, and this forms the current that turns on and off the Nixie tube. I think, yes, we got the other half here. I think this is really fantastic. They even put 2 in series here to compensate for the light or for the missing light resistance in those. Here we got 3, so of course you need to have 3, or that way 3. Oh man, it's just amazing how long they went to solve this problem. And of course this is because this was invented when things were made using radio tubes. So now they just continue to do the same kind of counter style. No need to invent a new counter. Oh no, we need to invent like a big time thingy to convert all this 4-bit system to drive a neon Nixie. Oh man, I love it. Here you see the different photocell matrix with the 8 different rooms and the different sensor elements, and it is just fantastic. Yeah, they were really smart to solve it back then. In case you haven't seen Nixie tubes before, I highly recommend you go and Google this technology. It's just impossible to take a picture of with this, but it's just amazing they could build these. So here, this first board that I took out from the, I think this is the timer section with all the different counters, because you can see we got that many different timer settings, and there are each of these, they contain a decade counter, right? Or times 10 divider, as you can say. And there is of course the original crystal non-divided. So that is of course how it works. So here, can you see what that is? I think there's a light bulb or a neon bulb, and then again a light sensitive element. So this is the gator. Look at that fantastic transistor we got down here. So it's a 2N169A. Oh, absolutely cute. Very, very old transistor. Isn't that just cute? Neon bulbs on this board just before the first counter. And again, the 2N169A. Oh, really, really cute, those transistors. I think I can prove this. See, this is the oscillator. 100 kilohertz. I don't know if you can read this on the screen here, but it says 100 kilohertz. So the next one is 10 kilohertz. Here we go. 1 kilohertz. Let's dial it down. 100 hertz. You guessed it. 10 hertz and 1. And of course the last one is gonna be, so this is, no, I haven't got a good contact. So it says 1 hertz. And of course the last one is gonna be 0.1. I'm just too lazy to wait for that. But anyway, so this is definitely the entire time-based system and clock oscillator right here. I still haven't really figured this out, because what the heck is this thing doing? Because it wasn't really the gate, because I think this one is the gate board, because this is what those LEDs are doing. One is doing the gating and the other one is doing the displaying, right? So that is kind of what is happening. Oh yeah, by the way, did you see this fan? It goes so slow, you can barely see it move. You can't hear it at all. And this unit uses 35 watts. Yeah, it does get hot. Maybe we should take a thermal image. So let's just look at this picture for a while. So this is the view, and I will be overlapping on top of this thermal images. So you see the different sections here. And then we're gonna go in the upper right with the time base, and then the center section with all the counters, and in the upper right with the power supply, and in the lower left with the input sections.